Alright, great. So in this video, we are going to now look at something called force. And under force, we are going to come up with an equation and then describe the units for force and that kind of stuff. You see, very, very exciting stuff, right? We've done motion. We've looked at the equations of motion, calculating the velocity and stuff like that. But in motion, we also have something called a force, because something would not move if a force didn't act on it to move. We know that from Newton's first law of motion, right? So something caused this thing to move. It is called the force. Or something is making this thing stop. It's also a type of force called retardation force or decelerating force. Or when you put on the brakes, there's a force that is being applied that is causing this thing to stop moving, right? When you throw something in the air, that thing is going to stop somewhere up there and then start falling down. Gravity is another type of force. When you step on a scale, to see how much you weigh, I'm putting weigh in quotes. I wish you could see my hands, but I'm saying weigh in quotes. It's because what that scale is measuring is your weight, and then converting that weight into your mass and saying, you weigh 50 kgs, you have 70 kgs. But actually that scale is measuring your weight and then converting the weight into mass. So let's see what this force is all about. So we're going to define, the first definition that we are going to have is something called momentum. And this momentum is defined as equal to the mass of an object times its velocity. That is just the definition of momentum. Momentum is defined as mass times velocity. It's usually written, I think it's a P. Sometimes people use a P, I think. So P is equal to mv. So it's just going to be mass times velocity. That's the definition, right, of this concept called momentum. When something is moving with a velocity v, and it has a mass of m, the momentum is given as m times v, right? So a 20 kg object, moving at 10 meters per second, it will have a momentum equal to 20 kgs, because kg, that is the SI unit for mass, times 10, which is the SI unit for velocity. It is equal to 200 kg coming from the mass, meters per second coming from the velocity. That is what momentum is. And these are the units for momentum, kg, meters per second. Those are the SI unit, I'm saying SI unit for momentum. Straightforward stuff, right? So now imagine this object collides with another object. So let's look at this object. There's our object. It's moving and it's 20 kgs and it's moving at 10 meters per second. And then it collides with another object, right? When it collides with another object, its velocity will definitely change, right? Its velocity is definitely going to change because they've collided, or not like definitely. Let me not say definitely, because there are some collisions where the velocity does not change, but let's just say the velocity changes for now. But yeah, most probably, like a majority of them is going to change. Maybe not in magnitude, but in direction. Like balls when they hit each other. If balls hit each other like that, right? If balls hit each other like that, it might be coming at 10, and then it leaves with another velocity of 10, but the direction has changed. So we can say the velocity has changed because the direction has changed. Magnitude might have been the same after hitting each other, but since the direction is different, velocity has changed. So here, when this object collides with another object, velocity changes. Therefore, momentum also changes, right? Momentum of this object, let's call it x. This momentum also changes because our velocity has changed. But from Newton's second law, you remember Newton's second law, it was saying the rate of change of momentum is directly proportional to the force applied. So the force applied is directly proportional to the rate of change of momentum. or in other words, change of momentum per unit time. Alright? So let's write that a bit nicer, because as physicists, we are also partly mathematicians, right? So what is the rate of change of momentum, or change of momentum per unit time? So change of momentum is written as this. This is a change of momentum, right? Divided, when it says per something, it means divided by that something. So per unit time, so you can just say per unit time. Let's just put the t for now. Or you can put as what is it called again? You can put it as delta t, or change in time, whatever you want to put. For now, I'm just going to keep it simple like this. It's just going to be like that, right? So therefore, but my p, I know what my p is. Therefore, my f is proportional to my mv over t, because I know that my p is equal to mv, like we discussed here. That is the definition of momentum. Momentum is mass times velocity. So that's what I did here. I just replaced my p with my mv. So therefore, f is directly proportional. Now let's look at this. Here we are saying a change in momentum. But what is really changed here? For our cases, there are special type of cases. But for our cases, the mass remains constant, right? The mass remains constant for our cases. There are some cases like rockets. You know, when a rocket is shooting up, first it has all that fuel when it's still on the ground in Houston, which is funny because that is my name. So, yeah, this is my name, Houston. You've heard Houston, we have a problem, because they'll be talking to like that space station in Houston. A rocket, when it's in Houston, let's just say at Cape Canaveral, I think it's called Cape Canaveral. I don't know how to pronounce that name. But that rocket, when it's waiting to go up in space, when it's still attached to all those pillars, right? When it's still attached there, here, let's just say here, this tank will be so full of fuel, ready to explode for it to go up to space, where I always dream of going. I dream of going to space one day. So it's so full of fuel. It's very heavy because of this fuel. But once it starts going to space, once this rocket starts going to space, taking me Houston from Houston Space Station. From Houston Space Station. At least laugh at that joke. From Houston Space Station, when it's now taking me, Houston, into space, that fuel will start going down. And as the fuel is going down, the mass of this rocket will start changing, right? So there are some cases where there is a force because the mass is changing, or the momentum of the object will change because the velocity is changing, and also because the mass is changing. These are special cases. We don't want to talk about these special cases. We want to talk about our simple cases. Our simple cases where the mass is constant. The mass is constant, so therefore, what exactly in momentum is changing? Momentum is composed of two factors, the mass and the velocity. So if mass is not changing, it means it is the velocity that is changing. So we can take out the mass because that is a constant. So the change is going to be delta V. And instead of putting everything under T, I'm just going to put the T under V, like that, and keep the mass outside. Right? It's still the same thing. It's still the same thing, right? I hope you all agree. Therefore, F will be proportional to, proportional to M. But what is delta V over T? Can someone tell me what that is? Yes, it is equal to change in velocity over time. You can say change in time. Remember, here I said you can write delta t. It wasn't going to really change anything. So if we put our delta t, it was going to be at the bottom change in time, right? It was going to be change in time, delta v over delta t. Awesome, right? But if you are paying attention throughout this whole series, what factor is this called? Change in velocity over change in time. That's exactly how we define acceleration, right? Acceleration is defined as the change in velocity over change in time. So which means this part here can be replaced by A, right? So now we see that our F is proportional to MA. And then, according to maths, to get rid of a proportionality sign, we put a constant. So our F is equal to a constant times MA. M being our mass, A being our acceleration, and F being our force. So in SI units, we're going to define something. That is our second definition, because we defined momentum up here, right? Then this is going to be our second definition. In SI units, we're going to define something called a Newton. Newton is how we measure force. Force is measured in newtons. Force is measured in newtons. Force is measured in newtons, right? So in SI units, 1 Newton, or written as 1N. So 1 Newton written as 1N is the force, is defined as the force required to give a mass of 1 kg, that is its definition, a mass of 1 kg and acceleration of 1 meter, I don't know what happened here, 1 meter per second squared. That is the definition of force, of the force of 1 Newton. A 1 Newton force is the 1 Newton is the force required to give a mass of 1 kg and acceleration of 1 meter per second. Let's plug these values into our formula. When we plug it into our formula, it says 1 Newton here, 1 is equal to K, we don't know what K is. What is our mass that we're talking about in this case? 1. What is our acceleration we're talking about? 1. When you clean this up, you see that therefore K is equal to 1. K will now be equal to 1. And since K is a proportionality constant, and proportionality constants say we do not care what your M is, we do not care what your A is, I'm just going to remain constant. That's why they're called proportionality constants. So no matter what your M is, no matter what your A is, the proportionality constant is the same. So in our special case where our M is equal to 1 and our A equal to 1, our Newton is defined there. We found that our K is actually 1. So in that formula that applies to anything, our K is equal to 1. So this is just going to be 1 MA. So F is equal to 1 MA. So writing it much nicely, this is a very, very important formula. F is equal to MA. Another very important formula for motion. F is equal to MA. I can call this maybe 4 on top of those 3 that we had for equations of motion, right? Let's quickly just look at an example here. So quickly looking at an example, it's saying if we have a mass of 200 grams, right? Mass of 200 grams acted on by a force which produces an acceleration. So M is equal to 200. Our acceleration is equal to 4 meters per second squared. What is the force? F is equal to MA. Therefore, my F is going to be equal to 200 grams. It needs to be in SI units. SI units are kgs. So this is going to be 200 grams divided by 1000 to put it in kgs. Multiplied by 4 meters per second squared. That is already in SI units, so that's fine. Multiplied by 4. You get that your force is 0.8 newtons. Easy stuff, right? So this is very, very important. F is equal to MA. In the next video, we're going to discuss a special type of force called weight that we've been talking about, hinting at. That is a special type of force called weight. We're going to discuss what weight is. And then from there, we try put everything together and see how far we've come.
Created with free version for non-commercial use.